All right, welcome back. Still in the space unit, and today we are going to explore that final stage in a massive to supermassive star where it just has so much mass. Instead of exploding into a supernova, creating a nebula, and going back into that stellar cycle, it creates our mysterious off branch of a black hole. So today we're going to talk a little bit about what are those parts of a black hole. How is this gravity that is created with a black hole so immense that it's able to hold the world, not the world, the most biggest structures in our universe together, galaxies? And how can we detect that black holes actually existed billions of years ago? And how do we know if they are in motion? And sometimes they can actually even collide. So we're going to talk about those different types of aspects with a black hole today. So at this point, you are obviously already understand that we've gone through our stages of a star with a nebula, a protostar, our main sequence star, and then we have our red giant, and we are talking about massive stars. So they're going to go through that red giant stage where they burn together hydrogen to helium, helium to carbon, carbon to nitrogen, all the way down till it gets to iron. But there's so much mass still left in that star. Instead of exploding outwards, it implodes. And that's what we're going to talk about today. So let me go ahead and move forward here. So sometimes you might refer to these as novas, meaning a new star. And so back in early Chinese history, the first nova was actually founded or recorded, written down, I guess I should say. It's been documented that some Chinese astronomers noticed that all of a sudden there was a much more brighter light coming from a certain area in the night sky. And over time, it's been renamed nova, which means a new star. Technically, though, it was not a new star, and this was that supernova that we've been talking about. So a nova occurs when a mass transfer binary star flares up, meaning that it gets super hot and starts to explode. So think about those Chinese astronomers that were watching this. This actually probably happened millions of thousands of years ago, and it's taken that light that long to reach the earth. So remember, once again, when we look at things in the night sky, we're technically looking at a past history of what's happening. That star could have already gone completely out, but we're still receiving that beam of light or radiation that is coming towards us. And it might take a couple of thousands of years to finally go out, depending on how far that star is in relative distance from us. White dwarf companion stars will sometimes go nova too, and you don't have to worry too much about that. I stole this from my astronomy class, so there's a couple of different things in here that might be slightly more in detailed. So the big thing that I want you to understand is that sometimes that we can have this disk of energy that is being attracted to another star. So here we have a white dwarf, remember, and that is the remnants of a very small star. And then we have a red giant here. And these red giants, remember that their outermost layers are really, really poorly put together or bounded together by gravity. So the white dwarf is able to suck some of that information from it or its layers. And sometimes this can cause a couple of different things, but let's kind of revert back to that supernova. So a single star that explodes and becomes extremely luminous in the process. So creating a whole bunch of new elements, fusing together heavier elements, creating a big nebula. However, now this is where we're going to kind of talk about where we're at, is that we have our black holes. And so you'll see some of these terms kind of pop up: solar mass. Just understand that is, we are comparing everything to our sun, and is it much larger? So sometimes black holes can be 3 to 0.2 times more massive than our sun. So really, really big. That is actually a small number. There's some that we'll talk about that have lots of solar mass. So a black hole is a remnant star greater than 3.2 solar masses. And instead of exploding into that supernova that we just talked about on the prior slide, it is going to implode into our black hole, meaning that it just, whatever reason, concaves on itself. So kind of think of almost like you've probably seen pictures where it looks almost like a whirlpool. It's actually a really poor representation of a black hole. Now that we kind of understand things, they actually more are is a spherical shape, and we'll talk about these different things. These stars leave a hole in space, meaning that space itself is considered to be on what we call space-time, which is just a flat surface, and things with mass are going to bend it down. Kind of think about if you've ever been to, I feel like I always see them at like Sam's and Costco, like where you drop a penny in and it kind of whirls around in that circular thing and it gets faster and faster and goes down. That's kind of what space-time is that things that have more mass are going to whirl it down into a cone. So even the sun bends down just the space-time a little bit, the earth bends down space-time a little bit. These supermassive stars just where we don't know where the end of that is. So these stars leave a hole in our space-time. And so a gentleman named Carl Schwarzschild was the one physicist who kind of first proposed the idea of black holes using Einstein's general theory of relativity, and that's that relativity, that space-time. Don't need to know all that, but I would like you to hear at least Schwarzschild's name because there is a portion of the black hole that actually is named after him. So he kind of took what Einstein had predicted and then used it to kind of help further it. So once again, this is like early 1920s where they're starting to come up with mathematically. Einstein mathematically was able to prove that black holes existed, but they didn't have the technology to actually see them at the time. And then Carl Schwarzschild also came up with and gave even more credit to it, where he came up with more ideas and even pinpointed where they would be in the night sky. Once again, didn't have the technology just readily available. It wasn't until Stephen Hawking came around that is when we were really able to kind of get some good technological data to kind of support this idea. And then actually it wasn't even until 2018 that we got our first picture of a black hole, which you'll see here in just a few. So, ta-da, there it is. So this is our first one that we ever took pictures of. It took the collaboration of many, many, many telescopes here on Earth they all pointed the telescopes in the same direction of the night sky where they knew this black hole was, and then started taking pictures. So you're probably like, well, I thought black holes were black. So what is happening here? So let's kind of talk about this. So once again, I want you to think that a black hole is dense enough that it's kind of emitting no energy, but it's taking it all in. Nothing can escape its collapsingness, if you want to think about it that way. So this redness and orange that you see behind it is actually almost like background light. So like think that I have a window behind me that's lighting the back of my head. You can't see it, but if I were to turn out the lights in my kitchen, you would still see light coming around me, and that's what this is here, is that this is the black hole here, and then this is light that is coming out around it from other sides. So it's not the best image, but it's our first image. So we are going to take that to the bank and hopefully learn more about it, and you're actually going to watch a video here in a little bit on the discovery of this and the collaboration that it took to kind of get it to where it is today. So that's our first image. So we have other technological ways of figuring out that they're there, such as stars orbiting around and then bloop, all of a sudden the star disappears. So that is one way which we were able to pinpoint that black holes were present. The other is now we can get some images of them. So a couple of different things with black holes. The first one of I guess talking about its characteristics is what we call the event horizon. And that is just the boundary of black holes in which matter and energy cannot escape. Meaning that once you kind of get stuck into that gravitational pull of that black hole, you're not getting out anymore. So Let's talk about our galaxy, the Milky Way galaxy. So it was hypothesized, and now it's pretty much confirmed, that all galaxies have a supermassive black hole in the center of them, holding everything together, which should make sense, because if you think about what we've talked about, we need something really supermassive that's going to generate enough gravitational forces to hold something together. And the universe is the Milky Way galaxy is a huge, huge structure. So we need something with a lot of gravitational force to do that. And so in the center, we believe there's something like this. Now, we still do have event horizon, but pretty much everything in that area has all been sucked down into whatever this black hole takes it. We don't know what. I know you're going to ask me that question. Well, Ms. Sparks, where does it go? There are many hypotheses on what happens once you've entered into that event horizon and we'll talk about this in a minute, it's called singularity, but no one really knows. Once again, these are structures that are far, far away, in which we are unable to travel to at this time, so we can only use satellite images and technology and mathematics to kind of help us figure out about it. So think about, we have one here in the center of our Milky Way galaxy, and like our solar system would be like way out on the one side. So we are not in what we call the escape velocity of no return. We are far enough out that we are not going to be captured in and then taken down into the endless doom of who knows whatever it is. We do understand that space-time is a continuation, so it is hypothesized that when you get closer to the event horizon, is that time does start to slow down, and it almost seems like things are moving backwards. I'm going to skip over this one. So two other things. The first one is the Schwarzschild radius, giving credit to Carl Schwarzschild, the distance from the center of the horizon, meaning that we are looking at this distance here. What is that distance that it's moving from? As long as you understand that it's, once you're stuck in there, you ain't getting out. And then finally, that last pinpoint is what we call a singularity, where it is infinitely dense. It is the most gravitational force that we completely understand. Wherever that star has finally collapsed down to, it's collapsed into the singularity, a point of complete density. And once again, we don't know what's happening there. To give you an idea, Cygnus is a black hole that you cannot see in the night sky, but it is visible to us in the constellation the Northern Cross, which you normally can see in the fall time. So if you are looking, you'll see something that looks like this, and you'll be looking for Etna, which is a smaller star, and Cygnus, is right there next to it. Once again, you won't be able to see it because it does not emit any energy or light. So what I really want to focus in on is what is called gravitational waves, which is ripples in space-time that come from merging black holes, meaning that at some point way back in early universe history, black holes would merge, and as they did that, they would send ripples out into our space-time continuum, and are still rippling because this is an immense amount of energy. And so scientists said we should try to build some type of technology that we can record these gravitational waves, and that they did. It's called LIGO, and we'll talk about it here in a minute. And back in September in 2015, they were actually able to hear those first remnants. And we talked about wave energy. So this is radiational wave that is coming from this very, very faint. You wouldn't be able to hear it from ourselves. But sometimes we need really big tools to hear really faint noises. So to give you an idea, this is the LIGO Center Laser Inframeter Gravitational Wave Observatory. We call it LIGO, and it is 2.5 miles long, the pipe that actually tries to pick up these radiation waves. and they were able to pick it up. So we're going to talk a little bit more about this. I have a couple of videos and questions that you're going to answer, but LIGO is a project with the National Science Foundation, and they were trying to figure out if we could actually pick up these gravitational wave energies, meaning that when black holes collide, they cause space-time to ripple, kind of like water in a lake, and we were finally able to pick them up. So go on to Canvas, and you're going to be looking for the assignment that's called Black Holes, and I'll